Good morning, everyone. Thank you all for being here. Today we have a special host, special speaker, actually. We have Guillem López from the Barcelona Supercomputing Center. So thank you, Guillem, for being here. And so it's your turn. Thank you.
Well, thank you very much for the introduction. As you have heard, my name is Guillem. I'm a PhD student. Happy PhD student. I'm about to graduate, so that is my smile. And I'm very happy today to present you some of my work in my PhD, which come with the same introduction. So, as you have already seen before, we are living in the accelerator era. So many vendors like NVIDIA, Meta, Google, anyone is investing in creating its own accelerators. And what I mean accelerators is hardware accelerators outside of the CPU or inside. These are just some news from the last years. And this has also created many startups that are developing its own hardware accelerators. So now we are getting more players in the business, and you can already see as well some of these accelerators. Okay. These accelerators were outside of the chip, but now we are also seeing inside of the chip. And when I say inside of the chip, for processors on the phone, on the laptop, or even on the Xeons from the Intel, they are also adding new accelerators. Why? Because, as you have already listened before, the end of the Scully created the multi-core era. And then, in the last decade, the diminish of Moore's law has also created that we have more space than ever. So why don't add accelerators? So now we are in multi-core plus accelerator era. In this fake SoC, we can see like a CPU with many cores and then many different accelerators. These multiple accelerators, we are especially targeting different applications like big data, genomics, but especially machine learning. And this creates many problems. Some of you may work on how to integrate the accelerators inside the CPU, how to connect them, how is it going to be coherent, non-coherent, and this in the end creates a problem on integration and verification. This is going to be part of the talk today. So I'm going to try to convince you some of the tools that I have developed to try to improve the verification of these large-scale hardware designs. So the talk is going to be about two tools. One is Gen 5 plus RTL, and one is called MetroBI. Gen 5 plus RTL has as the main objective to give you a framework. You come with a new hardware design that you have created in RTL, so System Verilog, PHDL, and you integrate it inside a full system simulator. Why? Because you may not have the whole SoC, you may not have complete hardware stack, FPGAs. Whenever you're in RTL, this gets kind of hard. So if you are in the early stages, it could make sense. And the full system simulator like Gen 5 already gives you like the whole software stack, like operating system, libraries. So finally, you are able with this framework to test the functionality of this RTL in a complete software stack, but also you are able to do early design space exploration. It's very easy to use framework. As an initial point, you bring your RTL module in VHDL or Verilog, and then you use one of these RTL simulators. In this case, I have only pointed out open source ones, which are JHDL or Verilator, but you could also use Synopsys, BCS, or QuestaC, provided that you bring your RTL model and then you create some C++ cases, classes. The second step is, once you have these C++ classes, then you combine with a wrapper that we provide. This wrapper gives you all these functions that you need to interact with this RTL module, and you create a shared library. You create a shared library, so later you can connect it with Gen 5, and with Gen 5 we also provide the classes, generic RTL object class, as we call it, which brings you all the functionalities that Gen 5 asks. So, for example, for example, talking with the memory hierarchy or virtual memory. We have evaluated this framework with different connectivity examples. The first two we have not evaluated, but it could be, for example, used to add a cache. You have a new design of a cache and you want to try it in an out of order. Maybe you don't have an out of order. The second example could be you want to test it in a network on chip. And of course, the interesting case for us today is you want to test an accelerator. We have used the NVDLA. It's the NVIDIA Deep Learning Accelerator. It's open source. It's on GitHub. Has good documentation. It's already on commercial products, so it's a robust RTL. And with this, we have tried to do a design space exploration on which type of memory would be suitable for the SOC. It's a little bit complicated, this chart, so I will try to explain it as best as possible. So the design space exploration that I'm going to show you today is about different memory technologies connected with an accelerator. And as a standard point, like we have used different NVDLAs connected to Gen 5, so 1, 2, and 4. On the y-axis, we have the performance normalized to an ideal memory. So we want to see which memory is better. On the y-axis, we have normalized performance to an ideal memory. So the better, the best. Then on the x-axis, there are the different parameters of the design space exploration that I'm going to show you now. And then for the evaluation of the NVDLA, we have used Google Net. It's like a kind of right now an old, kind of an old machine learning model. So let's just start with the different parameters of the design space exploration. We have different memory technologies, DDR4, 1, 2, and 4 channels, GDDR5, and HBM. All of these are grouped, so this represents every chart, and then all of these are grouped in the different maximum requests that we enable. You can see maximum requests as NSA charts, maybe it's more familiar to you. And finally, as I said before, there are different NVDLAs. It's a little bit confusing because it's like accumulated. So this performance number is going to be with 2 NVDLAs. This is 4, and this is 1. So it's hard to understand, but basically means that this is the performance that you're going to get with, for example, 4 NVDLAs. This is with 2, and this is with 1, all on the same bar. So using Gen 5 plus RTL, we're able to see some of these evaluations with different memory technologies. In our case, first, the maximum number of requests, as you can imagine, really affects the performance of the system. Then there are some memory configurations. This is quite interesting because for some configurations like DDR4 one channel, it works pretty well when we are enabling more MSA charts or maximum requests up to a point that it collapses and then slows down. So this is some useful information or insights that you can get with using Gen 5 plus RTL. So finally, as an obvious result, we can recommend only HBM or GDDR5 as better technologies when using more than 2 NVDLAs. Then the second use case that I'm going to show you today with Gen 5 plus RTL is for a more functionality test. So imagine you want to test a new RTL model. In this case, it's a performance monitor unit. This means you collect data and you can access for debugging purposes, for example, or performance purposes. This design was developed in-house at BSc, and it was actually tape out and used. So then we did a fairly simple evaluation of executing an application and then collecting data. So collecting the, I think it was committed instructions and also the cache misses. And then we are going, since Gen 5 already gives you this information, we're going to test the results from the PMU and the results from the Gen. So on the y-axis, we're going to see IPC in this case. On the x-axis, we're going to see time of the application. And we're going to compare. So we have used a simple application which consists of 3 different sorting algorithms. And we have also added a 1 millisecond like a slip between the 3 sortings to differentiate. This was fairly simple, but very interesting to see like the difference of the sorting algorithms. And there was no major differences on the PMU versus Gen 5. But also we could find something interesting, which was whenever the PMU had to reset, the PMU had some fancy features, and one of them was you were able to do interrupts after a threshold of reaching some point of like a metric. And whenever you were doing the reset of this feature, there were some cycles that you were losing information. And this was something that we could see from Gen 5%. So with this, I have tried to convince you Gen 5 plus RTL is an interesting infrastructure whenever you have this initial early evaluation of RTL modules, which you can put a modified Linux, you have a complete software stack, and model interactions of fairly all of the SOC components that you might need. We have provided 2 relevant use cases, and finally, Gen 5 plus RTL is suitable for SOC designers at early stages. It's also open source, so you can access, also, of course, ask me any question. With this, I think is the first part of the talk, and then I'm going to talk about the second one. This, for me, is a little bit more interesting. We got some interesting results that I will try to show you today. So RTL simulation, as you may already know, is really bad. Have you ever done any RTL simulation? I'm not sure about this lab. Okay. So you already know it's very slow. And especially today, our SOCs are increasing in size. So now it's common to see that we have tens, hundreds, or thousands of cores. These are some examples of the latest processors, and this translates into billions of transistors. So what happens with RTL simulation? RTL simulation is known to be really slow, and the vendors are not actually parallelizing. Only Synopsys VCS is sometimes parallelizing, but it's not clear what it's doing. On this chart, I will show you the simulation speed drops whenever we increase the size of the simulation, of the RTL simulated. On the y-axis, we have the simulation speed. On the x-axis, the multi-core size. So between 1 and 64 cores in this case. And we can see that as we increase the size of the multi-core, we're going to drop down the speed. And the reason is, if you're not parallelizing this simulation, you're going to require more and more computation at every second. So this is really bad. Only Synopsys improves a little bit that, but in general, the open source tools are not improving them. So the main motivation of this tool or framework is to improve this. Why? By using MPI. So we are proposing to use MPI, which is a parallel framework to parallelize any software. So let's start with a multi-core. It's released in this one. In this case, we have a network on chip of 3x3, so 9 tiles in total, and the chipset just means there is the memory controller and other fancy stuff that you have outside of the regular tiles. So by applying our methodology called MetroMPI, we are going to divide every tile computation of the RTL simulation in a different MPI process. And then also the chipset receives another MPI process. So this seems pretty easy. Let's try to understand how we do this. So first, you need to partition the design at latency-sensitive interfaces. This means understanding which are the connections between the tiles or any repeated hardware block. It doesn't need to be a multi-core. It can be any design that has many repeated hardware blocks. Then we identify the connections. When we mean latency-sensitive, this means that it's easier if you have any connection that happens at a cycle level. And it doesn't matter if it takes more than one cycle, but it happens at a cycle. If there are some, we can discuss this later, but if there are If it's not latency sensitive, it just means you may need to do more computation. It will still work our methodology, but requires more computation. If you have this feature between your interfaces, then it's pretty easy. You just need to separate the hardware blocks into different MPI processes and then communicate with MPI. So in our example before, we had 9 tiles. So just imagine one tile and another tile. You have many signals coming from one tile to the other tile, and then you group all the signals that go to one direction and then all the ones that go to the other direction. In the sense that you group all of these signals, and instead of having a signal in RTL, you group them in an MPI message. So this becomes software, but is following the same. It's following the same cycle accuracy. So you're not going to lose any cycle accuracy. You're also going to have the traces. You're not going to remove anything that RTL simulation is giving you. The methodology to evaluate this framework has been to use OpenPython plus Ariane, now CVA6, and we have simulated from chips from 1 up to 1024 tiles. The test bench has been an atomic synchronized token application. This means we have every core is doing some synchronization in order to exercise all the cores at the same time. And we have used 2 different simulators. One is Verilator, one is a big 3 RTL simulator that for MDAs we typically don't see. Then we have used a supercomputer. In my case, it's Marinostrum 4. It's a DSC. Although you could use it in any more or less data center. Just a point is that, so every node in the supercomputer has 48 cores, and since we are parallelizing and giving one MPI process per tile, this means that if we start with one times one, so one tile, so we are going to give one MPI process for the chipset, one for the tile. So this means you're using 2 MPIs, or 2 cores, and with it 1024, 125 MPI process. And you may ask, so is it worth it? Is the methodology giving you performance? So the reality is that yes, we were surprised by the performance that we obtained, in part because of Verilator, but also in the other big 3 RTL simulator, we also saw some big speedups. So in this chart, we can see simulation time speedup comparing Metro MPI with Verilator sequential. On the y-axis is the simulation time speedup. On the x-axis is the size of the multi-cores in this case. And we only tried until 64 because after 64, it was not compiling Verilator. So, sorry, do you see anything weird in this chart? So, for example, in this case, 4 times 2, this means 8 tiles. But we're obtaining 9.1 simulation time speedup. It's better than the idea, right? So this means that we're obtaining superlinear speedups. And although I was very happy to obtain that, my advisors were like, why are we obtaining? Why are we going better than the idea? So it turns out that by using MetroMPI, you are solving some of the problems that RTL simulations have. I'm going to try to give you.
I'm confused. You said that was the speed up in comparison with another simulator.
No, on the same Verilator. So in this case, we're using Verilator, and we are comparing MetroMPI against Verilator sequential.
So you have like Verilator on the in the MPI processes versus Verilator doing the whole thing.
So using by default Verilator, compiling and obtaining the performance, and then using MetroMPI. And when using MetroMPI, you're still using Verilator, but you are like encapsulating
on just the tile,
yeah,
instead of on the whole.
Was that clear?
Not really, but I'm going to pick it up.
Okay. So then, why is it improving MetroMPI so much, right? The reality is that RTL simulations are really hard. You can imagine when you're translating a Verilog, you're going to have a lot of if else's, and this is really bad for the front end of the host processor. So you're going to have a lot of ITLB misses and iCatch misses, and it's just by default of how you translate this Verilog or VHDL. And then the second problem is the binary size. The binary size of RTL simulations are relevant. So we did a little bit of debugging, and we found that ITLB and PKA misses are really bad in the sequential ventilator. We are getting up to 1, which is really bad. MetroMPI alleviates this, in part because the binary sizes are smaller. On the iCatch MPKA, it's something similar. We reach up to 30 in sequential, and MetroMPI alleviates this. Then on simulation speed, MetroMPI is not improving. You are still going at the same simulation speed that you can imagine in any RTL simulation. So this means kilohertz. But since we are improving on, you're reaching the same speed but using more cores, you're in the end getting more throughput. So the simulation is reaching up to 2.7 million instructions per second, which is something that you only achieved before in regular software simulators. We also characterize the MPI overhead. So whenever you are parallelizing any code, you're going to have some overhead by using an MPI parallelization. And in our case, you can see the compute communication ratio with different colors. Compute is blue and communication is green. MPI send is kind of stable because it's asynchronous, and MPI receive is synchronous. So this is why the MPI receive increases whenever we increase the size of the simulation. So the compute ratio at some point also increases. Then if we compare MetroMPI with the best solution so far of parallelization, which is the validator multithreading. Validator multithreading doesn't work all the times, but when it works, it gives you kind of good speed up. So we're talking about 4 and 5x, but MetroMPI outperforms this by a significant amount. Then some remarks. So MetroMPI is being used at BSc. BSc is the Barcelona Supercomputing Center and has been involved in many projects. So MIP, API, Sacantana, all of them have benefited from using MetroMPI. We have successfully done many design space explorations with MetroMPI, saving many hours of execution. And finally, personally, I'm also using MetroMPI for my research. I'm not explaining today, but I have also done some research on accelerators and connecting them, especially. So conclusion, MetroMPI is a general methodology that can be applied not only for cores, but any repeated hardware blocks. We overcome some of the problems found in RTL simulations, and we obtain exceptional scaling. Not only simulation scales up to 1024 times, also in simulation throughput and time scale. MetroMPI is also open source. It has benefited from different collaborations from UC Santa Barbara, one from Munich. It was a summer project in Google Summer of Code, and also ARM and Drag were other projects that benefited. And as a future work, in Gen 5 RTL, we are trying to test it with more accelerators, maybe support for HLS. We want to add more features for the framework. For example, the checkpointings of Gen 5 could be an interesting result. And for the MetroMPI part, we are considering trying other designs. So if you have a design with many repeated hardware blocks, please contact me. And finally, we also see a potential on automatically applying MetroMPI in, for example, validator or Synopsys. Funny fact is that we also tried to contact with Synopsys, for example, and we didn't receive the licenses that we wanted to try. And with this, I finish the presentation. And please ask me any questions that were not clear.
Thank you. Thank you.
you for your presentation, Guillem, and if there are any question, now it's the right moment for asking our speaker.
Yeah, curiosity. On slide 61, you show some overlap of MPI. Yeah, it's the same kind. I was wondering if that overlap is due to the fact that the data are not available, so it's dependency, or is it strictly MPI overlap due to the
It's a good question because I have not explained. So Metro MPI is actually stopping at every cycle. So at every cycle, you can imagine at the start of the cycle, you do the send, and then you do the receive. So it's kind of in lockstep. So as you increase the number of MPI processes, this creates like a stair kind of lockstep. So the MPI overhead is actually on the receiving.
Is there any other question? So there's no other question.
Yeah, I have a couple of more questions. Regarding validator, I mean the multi-thread validator, which is the difference in the approach that you use versus the approach that validator is using in multi-threading, splitting the task?
That's an excellent question.
Yeah, okay, good.
So Validator is using the threads.
Okay.
So this means you are limited by threads.
Yeah.
So if you have a node with processor with any threads, physical threads, you're only going to be able to scale up to the number of that thread.
Okay.
But you're not going to be able to use 2 shells, for example, or 2 processors.
Okay.
So MPI will give you that. You will be able to scale the simulations, and at some point you're using the fiber optic. So if you have a data center, you're going to use. So you're going to scale much more.
And regarding the logic of distributing the loads among the thread or the MPI process, which is the difference in the scheduling of, I mean, you are distributing cores or replicated Arduino blocks. Is the same approach of validator, or I mean, is it also validator having a similar super linear scale up, or
no? So validator does not scale that well. And it has a lot of problems when using the multi-threading. It has improved in the last version. So in version 5 and above, it was better. But it's not improving in the same way. So one of the problems is that Validator has a problem when finding the repeated hardware blocks. That is a problem. The binary size is not getting stable. It's actually increasing.
okay?
So I guess one of the parts on the algorithm that selects that is not working properly. Yes.
Okay. Regarding multi-threading versus MPI, as soon as you stay on the same processor, I mean, the thread should be lighter than MPI communication. So in the same processor, are you better than validator multi-thread, or?
Yes, and because the comparison is not fair. I mean, we are not using P-threads. So I should implement P-threads with the Metro MPI approach to actually test it.
Okay, but using MPI, you're better than validator multi-thread?
Yeah. You are better because also
because of the super linear scaling?
No, because of the communication with MPI, it's quite optimized even on the same processor. So it's not that. So the other one is lighter, sure. But MPI is not that bad inside the same processor. This is what I mean. It's optimized.
Like probably the communication step is better optimized than so synchronization that really is implementing.
Like if you're not using more than one node, you're not using fiber optic.
Okay.
You're using like an OpenMP.
Did you try the approach on the multi-socket processor or something like that?
Yeah, this is
okay.
by default. We scale up to 22 nodes.
Oh, okay, I see.
So I think by default every node had 2 shells, and of course there is like I think something like 64. So yeah, more or less here you get this is when you scale from one node to using more than one node, and there was a difference in performance.
Okay, I see. And just a last question regarding the first project. The Gen 5 plus RTL simulation, how much is the difference in actual simulation where, I mean, the accuracy of the result that you can get? I mean, because usually I implement directly on FPGA because I'm doing domain-specific accelerators, so I never investigate Gen 5, even if I would like to try, because it's more simpler to avoid to go in the implementation step. But my main concern was about the accuracy with respect to the actual execution on the physical board. And if you can also integrate some measurements such as energy estimation or similar stuff in the simulation step. So maybe I have a silly question, I don't know.
No, it's not.
I never moved to the simulator world.
I mean, it's one of the main complaints of
Yeah.
type or whatever full system. Like they claim it's cycle accurate, but in the end, there are differences with it.
Okay.
Of course, you can tune it. So you can tune it and get to, like, I don't know, many papers have shown 5%, 10% of difference. So you can reach a good accuracy and you gain a lot of like flexibility, but you're not executing, you don't have it.
Okay.
So if at some point you need to switch to FPGAs, but for faster early stage designs, exploration makes sense.
Okay.
Thank you. Now I know this. If you don't mind.
What?
Since the basic rationale behind the work was verifying and simulate things, I'm wondering how usable is it? Because you show us simulation that were working. Now, if I'm running a simulation, I'm not sure what I'm simulating is going to work. So I'm wondering how to use the tool to fix the things that I'm doing, and to use it really to simulate the things that I'm doing and to try to correct things if they were not working properly. What if the integration is not going to work as expected and all this kind of, if it's a verifying tool, how to use it to verify that what I'm doing actually not working as expected. Because to see things scaling, it's fine. But I'm using these also to check things, to simulate things. I'm wondering what if the simulation is not going to work properly? And how much of the things that you tested are not working?
So, for example, in the case of Metron BI, we have tested with course designs that are not working or are failing. Yeah. Like this is improving the speed. So I have used it, for example, in my last research to, and of course many, I mean, it's a design that I'm creating, so there are many bugs, and I have used it to actually speed up the process of getting the bugs reformed. So only by using like 1, 2, 3, 4, like a small SOC, you are already like going 4 times faster. So in my case, it has been like it's a faster approach to reach the debug, let's say. We have also used it. I mean, it's really complex whenever you are trying to put, for example, Linux with 4 cores and you have a bug in the FPGA. This is very complex, but we have actually also both Linux.
Because that was the other part of the question. Once the simulation is going to be fine, how to move for simulation to a real hardware?
I mean, I think this is something that you need to do in parallel always. That is tricky. I mean, this tool is not working on that direction. It's more on improving the before reaching.
I mean, the simulation that you are evaluating is behavior, right? Not post implementation.
Yeah.
I mean, you have to stop at behavior.
Yeah, it's behavioral. I mean, Accelerator, like only I think version 5 only allowed the synthesizable overlook. So it meant you require something that you're not doing any fancy Verilog, not synthesizable.
But you cannot go further in the post implementation here.
Then
I usually use Vivado, so I know Verilator, but I never use too much. So I stopped towards. I also use GL, also for behavioral simulation because you don't know the actual.
Yeah, it's behavior.
Okay,
so you're not going to have like weird glitches or.
Yeah, it needs to
that's true.
You cannot fit.
I think you have we're done this time, the questions, so thank you, Guillem, for your talk, and thank you all for being here. See you too when your next party is.
Thank you.
Thanks for coming.